Today we bring you the third video in the mass ranges of stars low, intermediate, and high video series. If you haven't watched the first and second videos in the mass ranges of stars low, intermediate, and high video series, please watch those videos before watching this video. Those videos are in the playlist 8 Stellar Properties: Mass, Luminosity, Temperature, and Chemical Composition. We invite you to stay until the last minute of this video. The nuclear processes occurring within stellar cores provide the energy that powers stars and drive their evolution throughout their lifetimes. Understanding these fusion reactions helps explain why stars of different masses follow such distinct evolutionary pathways and achieve different final fates. The temperature and pressure requirements for different nuclear burning stages establish the mass thresholds that separate the various stellar categories. Hydrogen burning, the longest-lived phase of stellar evolution, occurs through two primary mechanisms, the Proton-Proton chain and the CNO cycle. The Proton-Proton chain dominates in stars with core temperatures below approximately 18 million Kelvin, including the Sun and all low-mass stars. This process directly fuses 4 hydrogen nuclei to produce 1 helium nucleus, releasing energy equivalent to 0.7% of the original hydrogen mass according to Einstein's mass-energy relationship. The proton-proton chain proceeds through several subreactions, each requiring specific temperature and density conditions to occur at appreciable rates. The CNO cycle becomes increasingly important as stellar mass and core temperature increase, eventually dominating hydrogen burning in stars more massive than approximately 1.3 solar masses. This process uses carbon, nitrogen, and oxygen nuclei as catalysts to facilitate the fusion of hydrogen into helium, providing a more temperature-sensitive pathway that enables rapid energy generation in massive stars. The steep temperature dependence of the CNO cycle explains why high-mass stars burn their fuel so quickly and maintain much higher luminosities than low-mass stars. Helium burning requires core temperatures of approximately 100 million Kelvin and minimum stellar masses of about 0.5 solar masses. The primary helium burning reaction is a triple alpha process, where 3 helium nuclei combine to form carbon. This process involves an intermediate beryllium-8 nucleus that is highly unstable, requiring a delicate balance of conditions to produce significant carbon yields. Stars with masses below the helium burning threshold never achieve these conditions and evolve directly from hydrogen exhaustion to white dwarf formation. Carbon burning begins at core temperatures near 500 million Kelvin and requires minimum stellar masses of approximately 4 solar masses. This process fuses carbon nuclei to produce neon, magnesium, and other intermediate mass elements while releasing energy to power continued stellar evolution. Neon burning follows at temperatures around 1.2 billion Kelvin in stars with masses above about 8 solar masses, producing oxygen and magnesium through nuclear reactions with alpha particles. Oxygen burning occurs at core temperatures of approximately 1.5 billion Kelvin, again requiring stellar masses above 8 solar masses to achieve these extreme conditions. This process produces silicon, phosphorus, sulfur, and other elements in the silicon peak region of the periodic table. Silicon burning represents the final stage of energy-producing nuclear fusion, occurring at core temperatures around 3 billion Kelvin in the most massive stars. This process produces iron, nickel, and cobalt through a complex network of reactions involving alpha particle capture and photodisintegration. Beyond silicon burning, no further nuclear reactions can provide net energy output, as iron represents the most tightly bound atomic nucleus. Stars that reach this stage have exhausted all possible sources of nuclear energy and must face gravitational collapse when their cores grow massive enough to overcome degeneracy pressure. The progression through successive burning stages explains why only the most massive stars can synthesize the full range of heavy elements found in nature. The observable characteristics of stars provide astronomers with the tools needed to determine stellar masses, temperatures, compositions, and evolutionary states. The relationship between stellar mass and other measurable properties forms the foundation of stellar astrophysics and enables detailed studies of stellar populations throughout the universe. The spectral classification system, developed by Annie Jumpcannon and others at Harvard Observatory, divides stars into 7 primary classes designated by the letters O, B, A, F, G, K, and M. This sequence arranges stars by decreasing surface temperature, from the hottest O-type stars with temperatures exceeding 30,000 Kelvin to the coolest M-type stars with temperatures below 3,500 Kelvin. Additional spectral classes L, T, and Y extend the sequence to even cooler brown dwarfs with temperatures as low as a few hundred Kelvin. O-type stars represent the most massive main sequence stars, typically ranging from 15 to over 50 solar masses. These blue giants have extremely high surface temperatures and luminosities, making them visible across vast cosmic distances despite their rarity. O-type stars exhibit strong ionized helium absorption lines in their spectra, reflecting the extreme conditions in their atmospheres. Their main sequence lifetimes range from approximately 1 to 10 million years, ensuring that these stars are always found in regions of recent star formation. B-type stars span the mass range from approximately 3 to 15 solar masses, with surface temperatures between 10,000 and 25,000 Kelvin. These blue-white stars show prominent neutral helium and hydrogen absorption lines and have main sequence lifetimes ranging from 10 million to several hundred million years. Many B-type stars eventually evolve to become blue supergiants or other evolved massive stars. A-type stars, with masses between 1.4 and 3 solar masses, exhibit the strongest hydrogen absorption lines in their spectra and appear white in color. F-type stars, 1.04 to 1.4 solar masses, appear yellow-white and show prominent lines from ionized metals like calcium. G-type stars, including the Sun, have masses between 0.8 and 1.04 solar masses and display yellow colors with numerous metal absorption lines. K-type stars range from 0.45 to 0.8 solar masses and appear orange due to their cooler surface temperatures between 3,500 and 5,000 Kelvin. M-type stars, the most numerous in the galaxy, have masses below 0.45 solar masses and exhibit red colors with prominent molecular bands, particularly titanium oxide, in their spectra. The coolest M dwarfs approach the boundary with brown dwarfs and may show characteristics of both stellar types. The luminosity class system provides additional information about stellar size and evolutionary state, with Roman numerals indicating whether a star is a main sequence dwarf 5, giant 3, bright giant 2, supergiant 1, or hypergiant 0. This classification helps distinguish between stars of similar temperature but different masses and evolutionary phases. This video is getting long, so I'll stop here. Expect the rest of this in the next video. You can see more valuable videos by clicking on the card shown here. If you want to see our next video as soon as it comes out, subscribe to our YouTube channel and click the bell icon. Thank you very much for watching the video so far.